In this video, we'll continue our exploration of bivariate models, but this time we'll utilize a categorical predictor. We'll also continue with our analysis of bike share ridership in the Washington, D.C. area. In previous work, we explored the relationship between the number of rides per day, our response variable y, and the quantitative temperature predictor x. We modeled the trend in this relationship by the regression line riders equals negative 667.9 plus 57.89 times temperature. In general, we concluded that ridership tends to increase with warmer temperatures. Consider another potential predictor of ridership, weekend status. That is, how might the variability in ridership y from day to day be explained by whether or not it's a weekend, x. Take note here that the weekend variable is categorical. It's true if a day falls on a weekend and false otherwise. Though our approach will be different, we can also explore and study the relationship between our response and this categorical predictor. As a first step, as usual, we'll visualize the relationship. Recall that when visualizing ridership versus temperature, we utilized a scatter plot. This was possible since temperature and ridership are both quantitative, thus each day in our dataset had quantitative coordinates. We need a new approach for our categorical predictor. As a starting point, recall that we've visualized the univariate behavior in ridership a few different ways. Here, we're using a box plot. The goal is to include categorical information about weekend status into this plot. To this end, we can pull apart the information in the singular box plot into two separate box plots for our two categories. The box plot at left, where weekend equals false, gives us a sense for weekday ridership patterns. And the box plot at right, where weekend equals true, gives us a sense for weekend ridership patterns. In comparing these two box plots, we can explore the relationship between ridership and weekend status. The main thing we see here is that the box is situated higher on weekdays than it is on weekends. For example, comparing the approximate medians within both categories, notice that the median ridership tends to be higher on weekdays at around 4,000 than on weekends when it's around 3,000. Similarly, we can visualize the relationship between ridership and weekend status by pulling apart the singular density plot for ridership into one density plot per category. In doing so, we similarly observe that since the red density plot for weekdays is situated above or to the right of that of the blue density line for weekends, that ridership tends to be higher on weekdays. The median ridership is around 4,000 on weekdays and lower at around 3,000 on weekends. Ditto for histograms. We can create separate histograms for both categories and see that median ridership is again around 4,000 on weekdays and around 3,000 riders per day on weekends. These different visualization choices have pros and cons. For example, though it's a little goofier to interpret, the density plots here allow us to overlay the two densities, as opposed to the histograms here that are plotted in two separate frames, making it more challenging to compare. Thus, density plots, then, make it easier to visually compare the behavior in two or more groups. In contrast, the density plots are scaled to have an area of 1, so both of these curves are scaled to be roughly the same size. Thus, unlike the histograms, the density plots lose sight of the fact that we have fewer weekend data points. That's much clearer in our histograms, where we see a lot of data points on weekdays and fewer data points on weekends. In general, though, What we learn from each visualization is that ridership tends to be higher on weekdays than on weekends. That was step 1. In step 2 of our analysis, we want to specify this relationship using statistical models. As we did before, we can let y represent our ridership response variable and x our weekend status predictor. Yet we can't just jam category labels, true or false, into a numerical statistical model. What we can do is turn the true-false weekend categories into numerical ones and zeros. That is, we define x to be either 1 or 0. It's 1 if the weekend variable is true, that is, if the day falls on a weekend. And x will be 0 otherwise, that is, if our weekend variable is false, that is, the day is a weekday, or in general, it's not a weekend. Thus, we're essentially creating a new column in our dataset, x. X is 1 for any cases where we see weekend is true. And x is 0 anytime we see weekend equals false. Thus, we're not losing any categorical information by defining x as zeros and ones, we're just thinking about it differently. Once we make this switch to ones and zeros, we can now model the trend in the relationship between ridership and weekend status. This model is described by the formula y equals 3,925.53 minus 937.62x. Now, though this looks like an equation for a line, it is not. Since the weekend coefficient, negative 937.62, corresponds to a category, negative 937.62 cannot be interpreted as a slope. This makes sense if you think back to our visualization. It would make no sense to describe this trend by a line. In fact, a line is much more complicated than necessary to capture our simple observation that ridership tends to be higher on weekdays than on weekends. So what does the trend formula tell us? This is going to be a bit of a cliffhanger. You'll explore this question in class. In the meantime, I encourage you to challenge yourself here. Remembering that x equals 1 for weekends and x equals 0 for weekdays, try to see if you can use the visualization here to help figure out the meaning of the intercept, 3,925.53, and the x coefficient of negative 937.62. Again, I encourage you to give this a try, but certainly don't stress out about it. We'll talk about this in class as a group.